Hello, this is the solution to College Physics Chapter 3, practice problem number 31. So a rifle is aimed horizontally at a target that is 50 meters away. The bullet hits the target 2 centimeters below the aim point. So if you visualize it, it's being shot from here, this point here, and as it goes, gravity is taking its effect, bringing it down. But remember, it's traveling really quickly, so it's only going to have a fraction of a second to go down, and it moves down by 2 centimeters. All right. The key is that it's aimed horizontally, so the original angle when it left the rifle should have been completely parallel to the ground, basically 0 degrees to the horizontal. All right, so the first thing we want to know is how long was it in the air, what was its flight time, and then what was the speed of the bullet when it left the barrel. So the flight time, the first step would be, so think through the situation. In this case, we know that it left horizontally, and we know that as it left the pistol, we are assuming the pistol was aimed directly at the bullseye, and as it traveled, it lost some altitude due to gravity, and that altitude is this 2 centimeters over here. So we can use the fact that it fell 2 centimeters and that we know the acceleration of gravity, and we're assuming that the initial velocity in the vertical, v naught in the vertical was 0 initially. We know that gravity is the acceleration we're dealing with, and we're going to say that that's negative meters per second squared. So remember, have your sign convention ready to go. I forget myself. And we know that it fell a total distance of 2 centimeters, which we're going to convert to meters. So it's 0.02 meters. And that leads us to think about, well, which equation should we use? Well, if you see a displacement, chances are you're going to be using some equation similar to this. So we have delta y. And we know that it's going to be equal to the acceleration times the amount of time that it was in flight plus the original velocity in the y direction times that time as well. We also know that that means that this is 0 because the initial velocity in the horizontal was 0. And the only thing affecting it is going to be then the acceleration of gravity and the amount of time it had. So we need to rearrange this to solve for t, which is what we're looking for. Taking out, that step, you should come out with, through your algebra, something that looks like this, all under the radical sign. Then you can substitute in the numbers. 2 times negative 0.02 meters. Remember, this one would be negative because it's going to be going down in our frame of reference. And that's all divided by the acceleration of gravity, which is 9.81 meters per second squared. That negative here for the displacement is the key to canceling out the negative so you don't end up with any imaginary numbers. And that comes out to 0.064 seconds, right? So you might be like, well, that's really small amount of time. But then you step back and think, we're talking about a bullet that's traveling only 50 meters, right? So that's actually not very far. And at the speed of a bullet, which is really high, it makes sense that it would take less than a second for it to reach its bullseye. In fact, it's less than a tenth of a second. So that brings us then to the next question, which is, what's the bullet speed when it left, right? So we know how long it was in the air. We know how far it traveled. And that brings us then to, again, using the position equation, but this time we're talking about the change of position in the horizontal, so all of our values are going to be for the x dimension. So we set up our equation, remembering that that's going to be for the x direction. And in this case, we realize that the acceleration in the horizontal is 0, right? We're assuming that drag is negligible, especially the speed and distance. So we can get rid of that term, and that leaves us with the simple equation: distance equals velocity times time. And we need to solve that for the unknown. In this case, it's going to be the velocity initial when it left the barrel in the horizontal direction. We simplify our equation using algebra, and we end up with an equation that looks something like that. And we plug in our values. So we know it traveled 50 meters in the x-axis, and we know that it was in flight for 0.064 seconds before it hit the bullseye. That means it traveled excuse me, at 780 meters per second. Notice how we have two sig figs here. All right. So just to revisit, we used the kinematic equations for position. First for the y dimension in A to get the time, and then we used that time and our information for the x dimension to figure out how fast it must have been leaving the pistol as it was shot. That concludes the solution for Chapter 3, number 31.